Talk to you about a research paper called SQUAT, Subspace-orthogonal KV cache quantization. This paper caught my eye for a few reasons. It's put out by Red Hat AI Innovation. The gist of the paper overall is kind of dry and dense. Let me give you the gist first, and then I'll break it down into simpler terms, and then why exactly I want to showcase this particular research paper to you. So the key value KV cache accelerates LLMs decoding by storing KV tensors from previously generated tokens. It reduces redundant computation at the cost of increased memory usage. To mitigate this overhead, existing approaches compress KV tensors into lower bit representations. However, quantization errors can accumulate as more tokens are generated, potentially resulting in undesired results and outputs. In this paper, we introduce SQUAT. It first constructs a subspace spanned by query tensors to capture the most critical task-related information. During key tensor quantization, it enforces that the difference between the dequantized and original keys remain orthogonal to this subspace, minimizing the impact of quantization errors on the attention mechanism's output. SQUAT requires no model fine-tuning, no additional calibration dataset for offline learning, and is grounded in a theoretical framework that they develop. Breaking this down into more simple terms, let's take a look at their diagram here, right? So this diagram gives a good instance of what happens and what it does. So you have an initial input, and then from that initial input, they create a query subspace. And then they take this query subspace and then they shrink it into two dimensions. And then they find the distance that is orthogonal to the subspace. So the model, the model takes the input. Let's say what is an apple? And then that what is an apple becomes, in this instance, a we'll call it like a pocket universe for the model, right? Like a query subspace. And then so this pocket universe is a universe where it's dictated by the question, what is an apple? And then we then take that pocket universe, and then we take all of the information that is about that pocket universe, and then we encode it into two-dimensional space. And then from there, they find the space that is orthogonal to that subspace. So, honestly, think K-furthest neighbors, which is why one of the reasons why this paper caught my eye, right? Because they're doing that same kind of concept within this, but they're finding the orthogonal query subspace in this instance, as opposed to the orthogonal vector. And then so they're taking it actually a dimension further and a dimension deeper, which is interesting, right? But the same concept, they're finding so we have our pocket dimension is what is an apple, and then so if that pocket dimension exists, there has to exist a dimension that is the exact opposite of what is an apple, right? And then we know, as long as we know what the dimension is and the subspace of what is an apple of our universe that we create, we can measure what the orthogonal subspace would be. And it doesn't matter if we don't know exactly what it would equal. We can find out where it is via this calculation, and then that's essentially what we do, or what they do overall within this. So to me, this is a lot of interesting concepts overall, right? It's a lot that I've been saying and hammering on for a long time, right? Again, first of all, the concept that these models are training and are looking at essentially a abstract of your data and not the actual data set itself, right? That's number one. We're creating this query subspace. Number two is how much dimensionality plays into this. So it's dictated by dimensionality and geometry very specifically. And then third, how much distance matters within that, right? And then so like kind of like the bottom line, what this method does very simplistically, so it takes the initial concept, like your initial user prompt, it creates this query subspace, it shrinks that subspace down into 2 dimensions, and then that's not new overall, right? Like most of that's not new. And then what happens when you do that, and it's known, is that you get errors that result when you quantize that the response that way, right? Like when you're quantizing all of this way, you're going to get like some of it's going to be error, and then so what they develop within this is a system to essentially like detect that error within the query subspace, within the queue space, and then essentially make sure that the error is like orthogonal to each other, which is why they're introducing that orthogonal subspace, right? They try to make the error orthogonal to the subspace that's created. So interesting concept in and of itself. So if our query again is like what is an apple, and then we shrink like our that starts off as we'll say we're dealing with lots of dimensions initially, right? Let's say down to like the lowest amount of dimensions that we would be dealing with would be like 30 dimensions, and then so let's say it's between like 50 and 30 dimensions is what ends up being our query. Like hard to even wrap your brain around and understand, right? But then so within that, we need to get it down to something that can actually be understood by our brain, by a manifold, etc. And then so we want to get it into a 2D space. So that's what we do. We quantize it down into this 2D query subspace. So it's an abstraction of the space, right? Like it's so we're first of all taking our concept and then creating a space for it, so which is an abstraction, and then we're taking that space and then shrinking it severely from, we'll say, 30 dimensions down to 2, which is another abstraction. And then we're taking that and then we're saying we're creating another abstraction from that, which is like the orthogonal subspace from that, and then we're training the model on those last 2 abstractions in the string. And then the distance between those last 2 models in the string is what this process does, right? So that's what squat does in this instance. And then it's quantizing those tensors and then being trained on those tensors. Again, the difference between the query subspace and the like orthogonal query subspace. And then so what does that look like very specifically within code and in a model? So here's a simplification of this framework, right? It is a simplification overall of the squat framework. And then so first of all, we start off again, like it's lots of dimensions, right? So in this instance, we're starting off with 128 hidden dimensions. And then we have our subspace dimensions. So we want to take a sample of that. So we want to go from 128 to 5, and then we're going to go down to 2, right? And then we have our number of prompt queries. So those number of initial inputs are going to be 10. The number of bits is 2, so we want to quantize it down to like 2 dimensions in this instance. Then we have lambda regularization, which is important from the paper for the model, just as part of the mathematics. And then we have our blockwise quantization, again, 2 dimensions. So we're creating like an actual subspace. Like it's important that you actually think of these spaces, these digital spaces, as like actual spaces, like actual universes, actual pocket universes. There's a reason why I'm using those terminology and that terminology throughout discussing this paper, right? Because that's exactly what we're doing. So we're first of all simulating data. We're simulating data, and then from that data, we're calculating the query subspace from the data. So like I can't stress this again enough. It all comes down to abstractions. So the 2 best things that you can possibly do to understand and wrap your head around this concept completely is, 1, understand that we're dealing with actual space, actual dimensions, actual geometry that has impact on the space. The physics of the geometry of the space is dictated by it dictates the physics of the space. So whether or not it's Euclidean, hyperbolic, or fractal will make a difference within this. And then the dimensions of the space, the shape of the space, everything about it influences the space overall, right? So that's number 1. Number two is that everything that we're dealing with in this is we'll call it in the land of Platonic forms, right? And then understanding Platonic forms very deeply, and like Plato, like and then kind of what branches from there, and all from, like, if you dive deep, especially like if you start diving deep into postmodern philosophy within that, like, I mean, like Giles Deleuze is a very good uh, point of like postmodern philosophy within this. If you can understand this from both of those aspects, that's it gives you a good foundational starting point and place for these things, right? Like, a lot of people ask, where does my knowledge come from these things? A lot of my foundational knowledge starts from there, right? It's all like it's always a progression, right? Philosophy to physics to science and to proven theory, right? But it starts with philosophy to me, and then so having a deep foundational philosophical backing is important if you want to get into physics. And then so understanding, to me, like philosophy from starting, Plato, Aristotle, Socrates, etc., and then you move forward to like Descartes, and then you get like Marcus Aurelius, and then into like the more into like utilitarianism, and then like what prompts out of that, and then like Kant, and then like Nietzsche just kind of like kills the whole entire road. And then you get postmodernism, etc. But understanding like all of that track and how that progresses, I think, is very important concepts when we're dealing with these things overall. And you wouldn't think that that knowledge comes into play here, but it definitely does. So just pointing that out before we dive deeper into the code here. But then, so diving deeper into the code very specifically, the next thing that we're doing is we're simulating the query tensors from the prompt. So again, like the prompt becomes our universe. And then so like going like why did I just go on that like philosophical rant and that rant about philosophy? Like, here's why, right? Like I mean, I can't stress this enough. It's this, like, the best way to describe this is that the prompt becomes the universe, right? The prompt becomes the subspace. It becomes a pocket universe that we create. And then so whatever is in that prompt is the dimensions of that pocket universe. And then the whatever the dimensions of that pocket universe are inherently has an orthogonality to it. Orthogonal universe, like another one that exists, right? That is the exact opposite. And then whether or not you want to wrap your brain around it, does that actually physically happen or not? That's a different equation. To me, this is in mathematical terms, right? In mathematical terms, this is what happens and what plays out within these instances. And then so from there, the next step is to construct the query subspace matrix. So where like all comes down to matrix arrays that we construct, and then so like we're just using in this instance some very specific math from the paper. And then simulating key tokens, and then so this is where we get into like a very like where we're simplifying the model as opposed to like the actual squat framework there. And then we have we're quantizing the model, calculating the scale, so that's where we're shrinking it down into 2 dimensions overall. And then we're getting our projection matrix, calculating our simplified P inverse, like so calculating like all of these abstractions, right, is like the bottom line within this. And like all of this is like abstraction layers. And then so like going back to Plato, like the model isn't actually training on like, so again, like I can't stress this enough, like like what all of this boils down to and what we're doing is we're creating like shadow figures on like Plato's the cave, right? And then so the model is being trained on a projection of the data set and not the actual data set. So like the actual data set is being projected onto the wall, but the model can't look behind it and see the actual data set. All it sees is the projection, right, of the data set. And then so like Plato's allegory of the cave, it's the model is the prisoners sitting there watching the projection. And that's, I mean, that's what it is. It's the simplest way I can think of to boil it down to as to what goes on with the equation, right? And then you have your quantizations, so like a lot of mathematical functions within this, right? So then understanding math on top of the physics and the philosophy is very important in that as well. And then you come out, and then so this is essentially just like we're simulating and calculating our data in this instance. So we're simulating our data, and then we're calculating that query subspace. So then this is the actual, like, this is our universe, right? And then this is the shape of our universe. So it has a shape, and then it has actual dimensions, right? And then we can measure like the full shape and everything that would fall within the pocket universe that we've created there. And then so that's what we have there. And then from that there we want to shrink that shape, right? We want to make it all smaller. And then so that's kind of what we do there. And then so we're just applying quantization to it. And then we're like from there. So then the big thing is, again, that quantization. So we want to take the shape and we want to make it smaller, right? And then when we make it smaller like that and we squish it, we're going to create errors. And then so we'll have errors that will pop out. And then so let's say that we have errors that pop out of it. We want those errors to be far away from each other. If the errors are close to each other, it's harder for the model to measure, because the model is just like measuring and going through measuring geometry, the topology of this, etc., right? So like if we spread them out, like if we take so we have two errors that pop out, right? If they're close together, the model's going to trip up over them. But if we make them like very far apart like this, like it's just going to be like a little bump, and the model will just go over each one of them, and it won't correlate, like cause big problems. So that's what we're doing within like our big error correction within this, is just separating those errors, and then we just go through until we do that to the whole entire model. And then so what we do in this instance is, so we like our original like quantized. So this is our original shape of our dimension. Our quantized shape is smaller, but then we're doing a little bit of separation of those errors. So then our new shape, as opposed to the quantized shape, is going to be a little bit bigger, right? Because we want those errors to be a little bit further apart. And then so that's just what we're like. That's kind of the like real secret sauce and breaking down what this is doing overall, right? It's just doing that like normal quantization process, but then making that quantized universe just a little bit bigger than it typically would be, because we want to spread out and stretch out those errors within the equation. And then so that's basically the bottom line of the squat framework. But then just one last disclaimer: this code is a simplified conceptual illustration and not a production ready squat implementation. Just flat out pointing that out overall, right? That it's not like this. I am taking it like like in like 2 points within this. I'm taking I'm taking computational complexity and shrinking it down just purely because of compute, right? I want to run it on free Google Colab. So overall, here's the squat framework. Here's the squat paper. I think it's an interesting paper overall. Squat, subspace, orthogonal, KV, cache, quantization. This method wouldn't be possible overall if everything that I say on this channel, and I've been trying to tell you overall on this channel with regards towards like the geometry of these things, the physics, etc., weren't true. And so you can see it's being backed up more and more within this, right? And then it's a long road, because it's this is like, we're dealing with a area of mathematics that literally wasn't invented prior to 2017. Like all of this is like less than 10 years old as far as the actual mathematical field that all of this falls under, right? So it's kind of interesting to me and cool to be at like that cutting edge of it, but that's why I like it. And then so if you like this type of content overall, please like and subscribe. Thank you very much.